All right, we're going to talk a little more about the cottage cheese in the eyes and the parallel axis. Okay, remember we said this guy's going in two circles. One of them is around this pencil, and one of them is around that post. So it's got two circles, right? Now, one thing I want to remind you of is what we said about that cottage cheese. We said the radius of the lid itself was 5.75 centimeters. All right, I'm going to round that to 6-ish for this particular drawing. Then the distance that the center mass was to the post, that distance from here to there is 0.093 meters or 9.3 centimeters. I'm going to round that to 9-ish, okay? So I'm going to call that 6 and 9 simply because that could be, you know, 1.5 of those or 3 halves, and whatever way is easier for you to do your math, okay? So what I'm going to do is do the same thing. Calculate the eye of that cottage cheese lid using a parallel axis, the center mass plus the parallel axis. 1/2 mr squared, that's the radius of the cottage cheese lid itself. This md is the distance that that center mass is from the post that it's rotating around. All right, so this 1/2 mr squared isn't going to change. This will be plus m. Now that distance we said was 9 compared to that radius being 6. So what I'm going to call it is 3 halves. If you want to call it 9 over 6, you can, but it'll be 3 halves r. That whole quantity is the distance. I'm going to square it. Okay, and I'm going to add that to 1/2 mr squared right there. All right, so what I'm going to end up doing is keeping that 1/2 mr squared. This will be 9/4 mr squared. Want it? Okay. And so now I have to have those fractions come together. I can add 1/2 mr squared and 9/4 mr squared. If I take this and multiply it by 2 over 2, this will be 2/4 mr squared. That's an r plus 9/4 mr squared. So the I ends up being 11 over 4 mr squared. That's again if I ish that to be 9 and that to be 6. So now what I'm going to do is I'm going to actually do the math and get whatever I get. 11 divided by 4. I'm going to multiply that by the mass we got for the cottage cheese canister, or the lid, which was 7.41 times 10 to the negative third kgs, and then I'm going to multiply that by the radius again, which I rounded to 6. If I want to go back to real numbers, I'll call it 5.75. It really doesn't matter. I just want to show you how you'll end up getting pretty much the same number, 0.0575. I'm going to square that, all right? You multiply all of those together, and you end up getting 6.74 E negative 5 kilogram meters squared. All right, now that's ish. It's not perfect, but you see how that's 6.74 E negative 5? When we did the math on our last video, we got 7.6 E negative 5. That's when we used the actual numbers. So those two are ish the same. If we were in a perfect world, they would be the same if I didn't round those values or whatever. So a lot of times they're going to have you do math like this. They'll just give you a distance in terms of a radius, and they'll have you come up with the final I of whatever it ends up being in that fraction. I just did this math to show you how that ends up working out sometimes, okay? Now this is the same thing as a coffee, or I'm sorry, as a cottage cheese lid, but it's just a coffee lid. But I want you to realize that this center mass is right there where that lid is, or where that pen cap is, and that's the post it's rotating around. And can you see how where the post it's rotating around and that pen cap, they're parallel to one another, and it happens to be one radius away. It's the exact same type of thing. So if I were to ask you the eye of that guy, so for the coffee lid now, the I would be the I around the center mass plus the parallel axis. Okay, the I about the center mass is again 1/2 mr squared. The parallel axis is still md squared. That distance, though, is another radius, isn't it? So it ends up being 1/2 mr squared plus another m, and again, that distance is just another radius in this example. In that specific example, that is another r that I can square. So this just ends up being 3/2 mr squared. That's all. And another last example I can give you, just so you see that if one that's not necessarily a solid one, this is a hollow ring, isn't it? I mean, that's just the ring right there going in circles. The axis at which it's rotating is around this pencil also, and it's rotating around the post the same way we've done it before. Now remember, a hollow ring is just mr squared. So if I do one for the hollow ring now, for the ring, okay, this I is the I about the center mass plus the I that is the parallel axis. All right, the I about the center mass is just mr squared. That parallel axis is still md squared. So the hollow ring doesn't have a fraction in front of it, so it's an mr squared plus an md squared. What I'll end up doing is getting the radius of that ring by doing that, and then the distance away it is from the post by measuring that. Turns out this is what, 4-ish, and that was 12-ish, I think, if I remember right, or that was 3 and that was 12. I don't remember. This was 12. That could be 3 or 4. It doesn't matter. But if this radius of the ring itself happens to be 4 centimeters, then I will just leave it as that, mr squared. But this md now, if this happens to be 12 centimeters, then I'm going to call that distance 3r squared. Okay, so again, that's what if this is 3 centimeters and that's or if that's 4 centimeters and this is 12 centimeters. All right, not a big deal, but again, it's what that becomes is just mr squared plus 9mr squared, and so it equals 10 mr squareds, doesn't it? So if you knew the mass, just measure the mass. If you know the radius, measure the radius, square it, multiply it by 10. That's the resistance to rotation. So again, if this radius is fairly small compared to how far away it is from the axis of rotation, then the I around the center mass is fairly insignificant. It's only 1 out of the 10 mr squareds, okay? So that I can be calculated several different ways, okay? Now what I am going to now introduce us to is what happens if I's change. What can you do to change your I? Remember, this guy is just like the item on the record player, like I was showing you the other day, right? This guy is just going back and forth, isn't it? All it is the same thing as something on the record, right? So if this guy is going back and forth, it has an I. Its I is mr squared. All right, usually they just call it an ml squared instead of an r. But I want you to realize this guy's mass doesn't change. Bob can only be himself. But if I change his I, the way I can do that is change the length. So just get an idea. How many radians per second is this guy moving? I don't know either, but you know. But what if I change his length now? Just do something like that. You see how just changing the length changes the rate at which he's going in circles. That's what I want you to realize. All I'm doing is changing his I, and that results in a change in omega. I's and omegas are related. If you change an I, it will change an omega. Okay. Another example is, you guys remember these, don't you? What if one of these guys like this with the weight close to the centaur, right, was something like a baton twirler that the marching band folks use, and then they throw this sucker up in the air and it goes in circles, this thing's going nuts, and then when it falls down, boom, they catch it, right? Wouldn't it kind of play with your head a little bit if I give something like this to Glazer's engineering classes and I'm like, hey, Glazer, can you design something that'll make these C-clamps slide way out to the edge while this sucker's up in midair going in circles? And so while it's in midair going in circles, all of a sudden, boom, it ends up looking like this with the C-clamps way on the outer edge. Could you tell that this I now got bigger? I increased the I. And if the I got bigger, the omega would get smaller. So now in midair, this thing would just slow down. and then fall down, and you could catch it easier. Or what might even play with your head a little bit is if I throw it up like this with all the weight outside, and then Glazer's class somehow designs it and makes it slide inward, then it would start speeding up like crazy near the top, because now the eye looks like this, and then it will fall down and catch it. So if I can change the eye, the omega changes. Please remember that. And remember, I's replace M's, don't they, for rotational motion, and I takes the place of an M for linear motion. And remember what omega takes the place of. Omega for rotational motion is the same thing as the V for linear motion. So if I omega is the same thing as an mv, well then now I have some rotational momentum that I call rho mo, which I jokingly refer to as Tony. So we're saying hello to Tony. All right. I'll put this guy back. Another thing I want you to realize, what did I do? That pen, oh no, they're right here. All right, there's a Hershey Kiss on a record player. All right, a Hershey Kiss on a record player. Isn't that adorable? Now it's just going in circles. Okay. One of the things we talk about when we deal with linear momentum is what if this is off the turntable now, another Hershey Kiss slides into it, bangs into it, and they lovingly slide away together. That is an inelastic collision. It is linear, right? This is moving. If this is not, they combine, boom, that's a mass hole, and they move away together with some final velocity. This is a conservation of momentum issue, right? Well, what if I put the Kiss on the turntable? This guy comes flying in, boom, hits it. Now, instead of them sliding together in a straight line, they start rotating. I have given this guy some omega, haven't I? Or that other one did. So if that gains some omega, then gosh, there must have been some interaction between this, a collision, and a circular motion. So now I can get rotational or angular momentum based on linear momentum, and that's something else that we will allude to a little later on as well. Something else I'd like to remind you of is this is going in circles around that, right? This item flying in from the side is moving in a straight line, but we will end up calculating a rotational quantity for this guy moving in a straight line. One of my favorite sayings is, don't let the fact that something isn't rotating prevent you from calculating a rotational quantity. So as this guy slides in this way, boom, he's got Romo. This dude has Tony, even though he's going in a straight line. Boom, now he's going in circles, so linear mo becomes rho mo. What I want you to visualize is this arrow right there is a radius vector, radial vector. It is not a force, it is not a velocity. This is simply a radius vector, okay? Remember, an R with a little hat over it. It's the same thing as an I, a J, or a K. This is an R. Now, what if something else is moving in this way? That other Hershey's Kiss, like I was showing you, boom, moves that way and bangs into it. Now I have an R, and this is a velocity vector now. This is the V, the velocity of this Hershey Kiss. And you can tell these two arrows are perpendicular to each other, aren't they? That perpendicular means, ooh, gosh, we're going to use a sine function here. When these two bang into each other, they have a radius and a velocity that are perpendicular to one another. So there's an R, V, sine theta, okay? Sine of the angle between them. So if this guy were approaching this way, boom, it would still make the wheel go in circles, but not as efficiently, not as rapidly of an omega. Another thing I want you to remember, when you use the sine of theta, right, we call that a cross product. You have an R cross V. That's what I want you to realize, R cross V. Now, there is a direction associated with. What I want you to do is take your fingers, go in the direction of the R, curl them in the direction of the V. So R cross V. You see how my thumb is pointing upwards? That's the direction of Tony. If it's going the other way, something like this now, I want you to put your fingers in the direction of the R, curl them in the direction of the V. So R cross V, Tony is pointing downwards. Whenever you do a cross product, remember the order at which you multiply them matters. R cross V. R comes first, V second. We will do more examples of those as we go on, but that's the only right-hand rule from C this year. Next year, you'll get a lot more, but R cross V, wherever your thumb ends up is the direction of Tony.